this and say this is going to get a little bit technical, so if at any point you guys feel lost or that I'm not making sense or that I'm talking too fast, just like raise your hand and I'll stop and I'll like slow down a little bit, because this is something that I'm actually really passionate about, specifically in terms of I have this debate with lots of people. So just to preface this, what I'm going to be giving here is an argument. So I don't believe that there is a right answer to anything. What I'm going to propose here is my answer to the issue of renewable energy. So, let's start. Just his face. Or not. Thought it was better at PowerPoint. So this is the Longyangxia Dam Solar Park, please excuse my pronunciation, in China. It was constructed in February of 2017. It covers an area of about 27.7 square kilometers, or 13.6 square miles for you imperial people out there. And it has the capacity to power about 850,000 homes. Most people will look at this and say, wow, what a technical marvel. We're going in the right direction. Renewable energy is on the rise, and this is true. The world energy production system is changing. We're moving towards cleaner energies. We're reducing coal output in favor of cleaner natural gas. We're moving towards solar and wind specifically, as you can see by this graph. They currently represent about 10% of total world energy production, and they've been on the rise. So, would you mind skipping next? So today, one more. So today I'm going to talk about the 4 big renewable energies, specifically solar, wind, geothermal, and hydroelectric. And I'm going to explain some of the things that I don't think people really consider when you're talking about these energy sources. Because whenever you debate these sorts of things, there's sort of a presumption that these energy sources are perfect and they are the solution. And I would argue that there's a side that's not considered. So we'll start with solar energy. This graph right here shows the average cost of solar panels over the last few decades, and it's been decreasing. And you can see that today. The fact that the solar farm I showed you earlier is possible is because solar energy is cheaper. And you see it here today even. You see solar power, you see solar panels on top of homes, you see them on top of businesses. This is all possible because solar power has become a lot cheaper through mass production. The effect of this, however, is a lot of solar panels. What's the effect on the environment of having so many solar panels being mass produced? Well, let's consider that. You have to consider that when you're creating a solar panel, several toxic chemicals actually go into the production of solar panels. And solar panels have gotten cheaper because they don't have a long lifespan. So if you were to buy a high quality solar panel, the average lifespan of it would be about 20 to 25 years. That's the maximum lifespan if you're buying top of the line models. But the majority of solar panels on the market that make the solar farms like you saw before possible are cheap solar panels, which have a lifespan of about 2 to 5 years. And you have to consider that when you're manufacturing these solar panels, between the process of manufacturing and the process of disposal, what happens once these solar panels have exhausted their useful life? After 5 years, what do you do with them? The fact is, most of them will probably end up in landfills and polluting the environment. These chemicals that you see right here that go into the production of solar panels never decay. They are toxic forever, and they're a harm to the environment. And then considering wind energy. This is going to go into a little bit about wind energy as well as solar, because this sort of overarches with both of them. So the theoretical maximum power we can get from solar power is 1,400 watts per square meter. That's the amount of power that the sun puts onto a square meter of space for us. The theoretical maximum for wind power is about 1,800 watts. That's as much as we could possibly get from it on average over a year. However, technology doesn't allow us to do that perfectly. In practice, you can only get about 210 watts per square meter with even the most advanced solar panels that exist today. That's an efficiency of about 17%. And then when it comes to wind power, depending on the technology, it's 250 to 300 watts per square meter, an efficiency of about 15 to 20%. The overall question that's being raised here is, are these things space efficient? You have to consider that 210 watts per square meter is not that much. And then you have to consider the fact on how these systems work. So I'm going to go off on a little bit of a tangent here and explain how the US power grid works. The power grid of the United States and most other countries works on an on-demand basis. In other words, the exact amount of power that is required at any given moment is the power that's provided by nuclear power, solar, coal mines, coal plants, any other form of energy. It always meets demand exactly. The influence of this is that it's actually the reason why solar power, wind power, and other renewable energies haven't become so proficient. Because we can't control when the sun shines, and we can't control when the wind blows. As you probably guessed, the peak of power demand happens from about 5 o'clock in the afternoon to 9 o'clock at night when people are getting home from work. They're turning on their computers, they're turning on their TVs, and they're relaxing in front of any sort of electronic that's using power. Because of this, power demand peaks at a time when the sun, for example, does not. The sun gives out the most energy at midday. So how do we solve this problem? Because of this, we're not actually able to use solar power and wind energy to their maximum efficiency because they're giving out power when we don't need it. Because of this is why Tesla has actually been investing so much in battery farms like these, because you need these battery farms to store the energy when it comes in and use it for later. This is necessary if we're going to use solar power and wind power to the maximum efficiency. But this, of course, also has an implication for the environment, because the creation of batteries also involves toxic chemicals to the environment which never decay, including lead, cadmium, and lithium. Then, of course, there's also the matter of space. All wind power, solar power, and the battery farms take up a lot of space. So in order to power the entirety of the United Kingdom using only solar and wind power, assuming the space needed for the batteries as well in order to make it efficient, we would actually need to clear out 30% of the entire landmass of the United Kingdom in order to make that efficient. That's 30% of the United Kingdom, including deforestation, destroying of natural habitats, destroying all sorts of land. And because of this, I think that there's a serious argument in favor of the side that these power sources do just as much, if not more, to damage the environment as they do in the intention of saving it. Now I'm going to talk a little bit about hydroelectric. So the hydroelectric right now represents about 13% of total world production of electricity, and it's actually a really good method of storing electricity. Essentially what it does is you build up a dam by a river, and then you use the energy of the water flowing down from the upper reservoir to the bottom reservoir in order to gain electricity. The problems with hydroelectric power, however, are one, there's a net limit to how much we can actually get from hydroelectric power because they need rivers, and there's only so many rivers out there. Not every single country has access to these sorts of rivers. There's also a serious effect on the environment. We don't know what it does to freshwater fish or other animals that live in these natural habitats. And because of this, hydroelectric power is good, but it can't be implemented on the scale that is needed to address issues like climate change. And finally, I'd like to talk about geothermal. So, for those of you who don't know how geothermal energy works, geothermal energy essentially works by utilizing underground water reservoirs which are heated by the Earth's core. You build a geothermal reservoir above this reservoir, you tunnel down to the reservoir, and you pump cold water to the reservoir, whilst you pump warm water from underground up into the geothermal facility, and use the steam from this warm water to generate electricity. It's a very clean form of energy, and that's one of the biggest things going for it. The problems with it, however, are, again, it doesn't help the environment so much. So firstly, in order to construct facilities like this, the methods by which we access the underground reservoirs are actually very similar to the methods by which underground oil reservoirs are accessed through fracking, which obviously, as you all know, has a very serious implication on the environment. One such example is it actually causes surface instability. So in 1997, a geothermal facility was being constructed in northern Switzerland, and it had to be canceled after the digging to the reservoir caused a 3.4 magnitude earthquake in their area. So again, not an ideal form of energy production. And then of course there's the issue of distribution costs. Geothermal plants are limited in where the reservoirs are. We can't control where we put these plants. They may be far from population centers, they may not have access in certain countries, and because of this, they're very expensive. So geothermal energy is actually one of the most expensive energy sources in terms of cost per kilowatt. So what do? If all of these Hail Mary sort of ideal solutions aren't as good as we maybe thought, what's our solution? We all know that climate change is a serious issue, and we all know that it's something that has to be addressed immediately. So this little graphic right here actually shows the global temperatures based on 3 different scenarios. So the red line shows what would happen essentially, or a prediction of what would happen if carbon emissions worldwide continue to grow at the rate that they are now, and nothing changed at all. So if carbon emissions continue to grow at the rate they are now, we would have a net change in global temperatures of 4 degrees, which we all know is extreme. At least I would hope we all know. The green line is a slightly more tempered situation. That's assuming that we stop any growth and continue at the exact level of carbon emissions that we're at now until 2100. We'll see a net growth of about 3 degrees in global temperatures. And the final one right here is actually the prediction of what will happen if the entire world and all signatories of the Paris Accords strictly adhere to the policies it states out, and all the goals of the Paris Accords are achieved. So we can see that even by addressing everything that the Paris Accords did, we would only decrease it down by 2 degrees from its potential, which even then, that's a net increase of about 1.5 degrees from today, which is still an extreme amount, and it would still cause a lot of world issues. And because of this, we really need a solution now. That's sort of the fundamental argument here, is that climate change is something that is happening, and it's something that needs an immediate solution. The sooner the better. We need something that exists today, we need something that is economically feasible, and we need something that is realistically enactable. And this is where I would like to introduce you to my friend, nuclear power. So a lot of you may have some conceptions about nuclear power, and I would like you to put those aside for a moment while I explain the arguments in favor of nuclear power. Remember what I said originally. This is not the correct answer. This is just what I believe. And I just want you guys to entertain the argument I'm going to make. So, for those of you who don't know, I'm just going to make a brief explanation of how nuclear power works. So, nuclear power works through a process called fission, which is the splitting of the atom. Typically, you'll take a uranium-235 atom, as shown up here. You'll shoot a neutron at it to make the nucleus unstable. The nucleus will split into 2 smaller atoms, and this process will release energy. When this process happens at a very slow and controlled state, this is how a nuclear reactor makes energy. When this process happens in an uncontrolled state, this is how you get a nuclear bomb. And so how exactly do nuclear reactors extract electricity from this process? Well, it's actually very simple. Essentially what happens is you have a nuclear reaction occurring in the reactor, and this reaction generates heat. Then what you do is you cycle water through this reactor, heating up the water and turning it into steam. The steam is used to drive a turbine, which generates electricity, and the wastewater that goes through the reactor is what we know as nuclear waste. And this process, the only byproduct in terms of the nuclear production itself, is the steam, which is why nuclear power itself is completely carbon clean. So I'm going to talk a little bit about some of the benefits of nuclear power. First of all, in terms of capacity factor, nuclear power far exceeds any other form of power that exists today. It exceeds natural gas, coal, hydropower, wind by a factor of 2, and solar by almost a factor of 5. Capacity power is essentially the reliability of a certain power source. It is, in essence, it is how much power can you consistently take out from this power source at any one time. And then there's also the fact that nuclear power itself is extremely space efficient. The amount of space that you'll get from essentially one nuclear power plant will take up about a square kilometer, maybe 2, depending on the size of the plant. And most power plants output about 860, 870 megawatts, which is a serious amount, and these are the smaller ones. Also consider that nuclear power is a technology that has existed since the 50s. It is a proven technology, it is a technology that has existed for a long time, and it's a technology that's been perfected over time. Most nuclear reactors in the United States were built in the 60s and haven't been updated since then. So nuclear power is actually very, very safe, and this statistic I would like to show you here proves it. When most people think about nuclear power, they think of Chernobyl, they think of Fukushima, and it's true, nuclear power can be scary. But statistically, it's actually the safest form of energy we have. It's even safer than wind and solar, believe me. So why is that? It's because nuclear power itself is a very, very simple form of energy. It's an energy that doesn't require much maintenance, and it's essentially, if I put it into blunt terms, you sit in the control room and you just manage the reaction. Because it's been around for so long, nuclear power is economic, it's affordable, and it's something that is really, really safe. And if you think about it, when people think about planes are scary. Planes are very, very scary. When you see a plane crash on TV, you see the fire, you see the damage, and it's something that's scary. But then you remember that statistically, you are more likely to die in your car than you are in an airplane. It's actually the same thing with nuclear power. But then, of course, there's the downside of nuclear power, the waste. the waste that lasts 10,000 years, it's never going to go away. It's a problem. But I'd like to address some myths about nuclear power. So there are 3 levels of waste classification in terms of radioactivity and longevity of the waste being a threat to the environment. So there's low-level waste, intermediate-level waste, and high-level waste. The waste that comes out of a nuclear reactor is actually 95% medium and low-level waste. Only 5% of the waste, 5 to 3%, is actually high-level waste, which lasts more than 30 years. And that 5% of waste actually accounts for 95% of the radioactivity of nuclear waste. The argument here, or the point here, is that nuclear power, in terms of the amount of material or fuel used to generate power, actually uses the least. If you compare the amount of matter or production costs or sort of fuels that would go into any other sort of energy production, including solar, wind, coal, natural gas, all of that, the amount of physical mass that is used in the production of energy is the least in nuclear power. And because of that, nuclear waste is actually very manageable. Many reservoirs today are perfectly capable of holding nuclear waste for the next 500 to 1,000 years. However, again, there's the issue that it does last for 1,000 to 10,000 years. So, like I said before, no energy form is perfect. But I do think that we should consider nuclear waste because of these next statistics. So I'm just going to talk about what this looks like in practice really quickly. So I'm going to take 2 examples. I'm going to take France and I'm going to take Germany. So France has invested billions of dollars into the production of nuclear power plants, and at the moment about 75% of all power in France comes from nuclear sources. Whilst in Germany they've done the opposite. Germany has gone heavily towards the use of renewable energies such as solar and wind, and at the moment 50% of their energy is renewable, and of that about 30 to 35% is solar and wind alone. So what are the results of this? These are 2 countries with similar GDPs and similar economies, and what's the carbon output of each? Most people are interested to know that the carbon output of Germany is actually more than double that of France. And even the emissions per capita are again more than double, keeping in mind that the populations are not that dissimilar. That's not the only thing, however. Regarding the costs, Germans actually pay almost 1/3 more for their energy than French do. The net effect here, nuclear energy shows to be almost twice as clean as the renewable energies in total, considering the production and disposal of other forms of energy. It's twice as clean, and it's also less expensive. It's economic. It's cheap. It's something that's feasible. And because of this is one of the reasons why I argue that nuclear power is the best solution that we have for what we face today. Because like I said before, climate change is something that needs immediate action. Nuclear power is not perfect. It's not. But no form of energy is. Nuclear power is the most feasible form of energy that we have today that theoretically could be implemented within 10 years. But it actually gets better because there's a better solution. And this is where I'd like to introduce you to a friend of mine, thorium. So I'm going to explain the difference between thorium and uranium. Thorium is actually an alternative source of fuel to nuclear reactors than is uranium. The reason why most nuclear reactors today use uranium is because of weapons. During the Cold War, it was simply effective and efficient to just produce the same fuel source for your power and for your weapons, because the uranium and decommissioned nuclear weapons could be used in nuclear reactors, because uranium is easily weaponizable. Thorium, however, is not. Thorium is a much less reactive chemical than is uranium, and it requires a much lower degree of enrichment in order to be used as a nuclear power source, and it's not easily weaponizable at all. There's also the added benefit that thorium is much less fissile than uranium. Fissile basically means, in terms of the fission reaction I talked about earlier, how stable the fission reaction is of a uranium or an object undergoing fission. The reason why the Chernobyl accident happened is because uranium is an extremely fissile substance, which makes it very good for weapons. If a fission reaction is started in a block of uranium, the fission reaction will continue on its own. It will perpetuate itself, which makes it very good for weapons and easier for nuclear power plants. But the problem means it's harder to control. And the reason why Chernobyl happened, if any of you watch the show, is because they couldn't control the reactor. Thorium, on the other hand, is not fissile on its own. If no source of neutrons is posed for the chemical, then it won't undergo any fission reaction whatsoever. So in essence, what this means is that where there's some problem to occur in the reactor, they simply stop the flow of neutrons and the reaction itself stops, making thorium much, much safer than any other nuclear reactor using uranium today. And actually, India has invested heavily in thorium reactors, and that's currently the place where thorium reactors exist in practice alone today. And finally, the biggest benefit of thorium is its fission products. Whilst the fissile products of uranium will remain radioactive for up to 1,000 to 10,000 years, the fissile products of thorium will be less radioactive than those of uranium within 300 years, which is a lot less than 1,000 to 10,000, and a lot more manageable. We don't need to have a perfect energy source that's going to last us forever. We just need to have an energy source that's going to last us until we have something better, because we need something better. We need something that can address the problem we have today. And this is why I think thorium is the solution. This is why I think nuclear power is the solution. Theoretically, the entirety of the United States could switch to the use of thorium reactors and be completely carbon neutral in terms of its production of energy within 10 years. It's realistic, it's achievable, and I think it's a solution to our climate problem.